Howdy. Welcome to the Smart Grid Center webinar titled Assessment of an AC Interconnection of the North American Eastern and Western Electric Grids. I'm Andrea Kishney from the Smart Grid Center of Texas A&M Engineering Experiment Station. Before introducing the speaker, let me ask you to please keep your mic on mute and hold voicing your questions until the end of the presentation. However, you may also type a question into the Zoom chat box anytime. The presenter today is Dr. Tom Overby, Chair Professor at Electrical and Computer Engineering and eminent professor with Texas A&M Engineering Experiment Station. He's also the director of the Smart Grid Center. Prior to joining Texas A&M 5 years ago, he was a chair professor at University of Illinois at Urbana-Champaign, and he has a wealth of industry experience. Dr. Overby is the original developer of the PowerWorld software and co-founder of PowerWorld Corporation, and he is also a member of the National Academy of Engineering. Dr. Overby, take it away.
Hey, thanks, Andrea. As she said, I'm Tom Overby. I'm a professor here at Texas A&M, and today I'm going to talk about a study that we did for some utilities that looked at an AC interconnection of the two largest grids in North America, the Eastern and the Western grids. But since I'm here in College Station, was definitely affected by the events from last week, I'll briefly mention some of my take on what took place. So first of all, I'd like to acknowledge the support of a lot of different people and a lot of different entities. This project was funded through PSERC by SPP. They're a utility that oversees the operation of the grid, primarily in the central part of the U.S. and increasingly in the western part of the U.S. The slides here have contributions from many people, including my students, postdoc staff, so I appreciate that. We use PowerWorld Simulator version 22 to do the analysis and visualizations that I'll be presenting here. And of course, I have to say that the views expressed here are my own and do not necessarily represent the views of any other person or organization. So the overview, I know we've got a lot of students on the call, and electric grids get in the news for oftentimes bad reasons because we've failed in some way. But I want to emphasize that it's a really exciting time to be in the electric power field. There's a lot of transition going on. There's a lot of opportunity for students. We're integrating in large amounts of renewable generation. We're changing the load, adding more electric vehicles. Customers are getting more choice. There's a lot of new technology being used in the grid. So there's lots of opportunities for innovation in how the grid is operated. And this presentation is going to cover one potential innovation, which is actually an integration of the North American Eastern and Western grids. I should say that the slides will be made available afterwards. So if I go through something pretty quickly, you can pick them up afterwards as well. This is a view of the big grids in North America. We have 4 large interconnects. The largest is the Eastern Interconnect, which actually comes over into the county I live in Texas, but it goes all the way from Canada down to Florida. The second one is the Western Interconnect, which actually covers 3 countries, Canada, most of the western part of the US, and a little bit of Mexico in Baja California. The third one is ERCOT, which has been in the news recently, which is wholly contained within the state of Texas. And the fourth is Quebec. So we'll be talking about the ones that are in the US today. If you are wondering, where do we get our generation from? Turns out that there's a lot of public information that you can access. A good set of information on electric generators in the US comes from what's called EIA Form 860. It lists the capacity of the different generating plants, tells their latitude and longitude, a lot of different information about them, including their fuel type. So what I did is I just made up this visualization to show you where the generators are in the country based on fuel type. Red is nuclear, black is coal, brown is natural gas, blue is hydro, green is wind, and yellow is solar. The ones that are growing most rapidly right now are wind, solar, and to some extent, natural gas. Since I was in Texas and it's been in the news, I wanted to show you a zoomed in view of this part of the world. We have a lot of natural gas. We've got 4 nuclear power plants. I should say the image here shows it at a substation level, not at an individual plant level. So we've got 4 nuclear reactors in the state that are located in 2 locations. One of those actually did fail as a result of the events from last week, one of the ones down on the Gulf there. We've got coal, we've got natural gas, and we've got wind. But the study here was really focused not on Texas. It wasn't focused on ERCOT at all. It was focused on from kind of the northern part of Texas up into Canada, because we were looking at interconnecting the eastern and the western grid. So I'll get to that in just a second. Before I do, I did want to add a few comments on our Texas cold wave, which started on Valentine's Day. Here in College Station, a lot of times in the winter, we have quite nice weather. For example, right now it's maybe in the mid 70s. On Valentine's Day, our average high was supposed to be 65, or average high was 65, and the average low was 45. The coldest we've ever had here was -3, and all these values are in Fahrenheit. That occurred about 70 years ago, I guess. Our coldest February temperature was also close to 70 years ago. That was 5 degrees. Last time it hit the single digits here was in 1989. So that would have been 30 years ago. On February 15th, it was 9 degrees Fahrenheit here, and it was very windy. And then the next day it got down to 5 Fahrenheit. That's a picture of the road outside of my house. And I grew up in Wisconsin and then spent 25 years in Illinois. And that is a very typical picture for February in the Midwest. My Wisconsin roots would say that's a nice winter day. It was maybe, that was in the morning. It was maybe 10 degrees out. It was kind of windy, but it's like it wasn't too bad from a Wisconsin point of view. The problem is, from a Texas point of view, is our infrastructure is just not designed to handle this. And the Saturday and Sunday before, I was looking around our house to see how well are our pipes insulated. And I found out I had a lot of uninsulated pipes in my attic that I quickly tried to cover with whatever I could find to insulate them so they didn't break. And the problem with what occurred is we had a blackout and we had a lot of pipes break because it occurred on one of the coldest days in the last couple generations. So I was actually, because I'm a power engineer and I knew that in Texas we use a lot of electric heating and it was really cold Sunday evening. So I was watching the electric demand from ERCOT, and on Sunday evening between 6 and 7, ERCOT actually set a maximum for their all-time winter peak demand of about 69,000 megawatts. That's in contrast with 74,000 megawatts that we would have for max in a summer day. But it was 4,000 more than we had ever had in the winter, and that was just 3 years beforehand. So I was wondering what would go on. Well, what went on is at 1:25 a.m. on Monday morning, ERCOT had to do about 10,500 megawatts of load shed because they had a lot of generation that was forced off the system. They went to an EEA3 emergency condition, which ended on Friday, February 19th. By then, our temperatures were much more on the warmer side, although they were still close to freezing. So it wasn't great by Texas standards, but it was much better than what it had been. It was really bad. And as I've been talking to people, some people have had it really bad. Here at A&M, we have had some significant damage to our buildings, some damage to equipment, primarily because the pipes froze and they broke. So a lot of that is water damage. Many Texans lost power and water for days, and they had large amounts of damage. I've seen that on the news. I've seen that in talking with people here in town. Others did not lose power. You may have kept your power, but chances are you probably lost water. Although the water loss that we had here had actually taken place after the worst of the temperatures were passed. So a lot of load was lost, but ERCOT itself continued to operate. What I found very scary is that ERCOT reported that they were seconds and minutes from a total collapse, and I think that would have been a catastrophic scenario. We lost a lot of load, but we kept a lot of load on as well, and then other load went to rotating blackouts. If we had lost, or if ERCOT had lost their entire system, everybody would have lost power. A lot of backup generators would have failed. A lot of critical infrastructure would not have had electricity, and it would have sustained damage beyond what we already got. I don't know the details, but I do think there are heroes out there among the ERCOT people and among the utility operators, the engineers, the field personnel. While most of us Texans were not out driving because I've learned that we don't know how to drive in snow, a lot of the utility people were out driving around trying to restore power because we had got icing. People in the control centers were there. I don't know the details, and that will come out with the investigation, but I think there were some heroic actions that took place. I will say that throughout this whole pandemic, I have been very glad that we have not lost our electric grid, particularly early on in the pandemic when we all had, we were all dealing with the shortages of toilet paper and other things. If we had also lost the electric grid at that point, I think what is a bad situation, and COVID is a bad situation, would have been horrible. Okay, so we've got 3 grids in the US, and ERCOT is the only one contained within a single state. So we might say, why is ERCOT separate, or why are we separate here in Texas? ERCOT operates asynchronous from the rest of North America. So that means with the rest of the country, but we do have DC ties. We have DC ties going to the Eastern Interconnect, and we have DC ties with Mexico. The advantage of this is we avoid some federal regulation because of that. The legal basis for this avoiding federal regulation is complex. And I am an engineer, I'm not a lawyer, I'm not a regulator. So I'm not going to tell you all the details on how this works and how we can interchange electricity in the form of HVDC, but not in the form of AC. That's what it is right now. Whether it will continue to be that way, I don't know. So what is special about HVDC? Well, as the name implies, it's direct current as opposed to alternating current. If you watch a movie like Current Wars that came out talking about the history of the electric grid, Edison started out with a DC system, and then Westinghouse and Tesla showed the advantage of an AC system. So most electricity is transmitted in the form of AC, either at 60 hertz or at 50 hertz, with much of the world at 50 and us here at North America in 60. The high voltage, or HVDC, is used for bulk power transmission primarily. The advantage of it is we avoid something called reactive power. It gets better to transmit power long distances if you can use direct current as opposed to alternating current. And it is also better if you have to transmit your power long distances in a cable, such as you might have in an undersea cable or sometimes in underground cables. HVDC is sometimes used within a single interconnect, and one of the most famous ones is the Pacific Intertie in the Western grid that takes power from close to the Oregon-Washington border down into Southern California. Sometimes it's used to transfer power between interconnects. For example, we use high voltage DC to bring power from Quebec into the Eastern Interconnect in New England. And sometimes it's used in the form of back-to-back HVDC. And that is where you use it to transfer power between AC interconnects. And with Texas, we're doing some of that with the Eastern Interconnect. We're doing some of that with Mexico. On this study that I'm going to talk about in just a second, we did that. We've got back-to-back DC between the Western and the Eastern grids. An advantage of HVDC is it can be controlled quite quickly on the order of milliseconds. With AC, we can control AC at least at a more interface level, but it takes on the order of seconds to tens of seconds to do it. If you're interested in what's coming in Texas, potentially, there is something known as the Southern Cross HVDC transmission project. The goal of this would be to build a 400-mile long, 500 kV high voltage DC line between kind of Tennessee, Mississippi, Alabama border region, bring it to the Louisiana-Texas border, and then bring it into ERCOT with a potential capacity of 2,000 megawatts, which is much, much, much more than we currently have for a transfer capacity between ERCOT and the other interconnects. And I've included a link there in case you want more details on it. I think it might be operational in 2022, but it wasn't clear from what I was looking at there. Okay, associated with this cold snap, the idea of resiliency has come up, and people will say, how come our grid couldn't handle that cold? That gets into the idea of how can the grid deal with what I would call high impact, low frequency events. This ties into electric grid resiliency. I've worked in this area for a number of years, and I think it is extremely important, but it's often an overlooked aspect of the operation, design, and research associated with electric grids. I will say, anytime we design and build an engineering system, there's a trade-off between risk and the mitigation costs to deal with that risk. And we certainly can better insulate our generating plants, just like I could better insulate my house. And in doing so, you're balancing risk versus the cost to do that. There is a great reference on this. It's a free 2017 report that came out from the US National Academies titled Enhancing the Resilience of the Nation's Electricity System. If you're interested in this topic, I would strongly encourage you to get that publication. If you just Google it, you'll find it's very quick to download as a free PDF. And that document does mention the 2011 Texas cold snap and says that, hey, as a grid, we need to be more resilient, more prepared for these events. But it's not just cold snaps. There's a lot of other events that we need to prepare for. Okay, a quick commentary on electric grid AC frequency. In an AC interconnect, usually we keep the frequency very close to desired, which here in North America would be 60 hertz. That's done by constantly matching the generation to the load. If you have too much generation, the frequency increases, and if you have too little, it will decrease. So one of the things we power engineers do, and one of the things that we did a lot of on this project, was to look at the dynamic response of the grid to large events, and a large event might be the loss of a significant amount of generation. The graph there shows how the grid frequency will respond when you lose a large amount of generation. And what happens is, in steady state, everywhere in the grid has the exact same average frequency. But during disturbances, those frequencies can vary as the grid actually oscillates. And I'll show you some examples of that in just a second. If we lost a large amount of generation, what would happen is the frequency would start to drop. As the frequency starts to drop, what's going on is we are getting energy from the inertia stored in the rotating masses of the generators. usually there's enough energy there that within seconds, the frequency starts to stabilize. If it doesn't, if the loss of generation is too much, then we have relays out there that will drop load if the frequency goes too low. And each interconnect has relays set for particular frequency cutoffs where they will drop load if it goes too low. And that helps to arrest the frequency decline and hopefully stabilize the grid. When the frequency starts to come back, actually, as it's coming back, the generators have governors on them. These are automatic control devices that increase the mechanical power into the device to make up for the lost generation somewhere else. So within seconds, we get the governor response. That does not restore the frequency back to 60 hertz, but we have another control system known as automatic generation control that over the course of many seconds to minutes will restore the frequency back to 60 hertz. And on this project, because we were connecting the eastern and the western grids, we were modeling all of these different response mechanisms. Okay, so the east and the western grid are separate, but it hasn't always been that way. Actually, for a few years, from 1967 and in the 1970s, the grids were connected. I got one of the papers there that it's from 1970 that's talking about the nation having the largest synchronous network that now extends from coast to coast and includes 94% of the US generating capacity. Julie Cohn, and I misspelled her name there. There's no E in her last name. She wrote a great article in IEEE Proceedings, I guess 2 years ago, that talks about this. If you're a power person who's interested in the history, that's a wonderful article to read. But the grids have been connected. That's a schematic of the grid from 1970. If you don't know much about electric grids, it probably looks like just a bunch of scribbles across a map of the US, but those scribbles are high voltage transmission lines. The key takeaway is in the northern part of the central part of this country, like Montana, North Dakota, South Dakota, Nebraska, there's actually lines that go from east to west and join it together. That's because for a few years we were connected. If you look at the bottom part, the Texas part, Texas was separate at that point as well. Okay, before I go further in the presentation, I did just want to mention the concept that's known as critical energy electric infrastructure information, or what we call CEII. After September 11th, information about the grid became more restricted, and the concept of what's called the CEII was developed by FERC, which said that you can't get access to all the information about the grid unless you have some reason to do that. And if you have reason for that, to have access to that information, you have to be, you can't share the CEI part. So in this project, we used a lot of CEII, but I have been very careful in the presentation to set it up so it does not contain CEII. I will say that CEII is not associated with the general location of critical infrastructure. That's why the EIA 860 data can show you the exact latitude and longitudes of the generators, or you can find out the locations of transmission lines. That is not CEII. It's just when we start talking about the engineering response that it gets more CEII potential. Okay, so the summary of the presentation is we took these two large grids and we got the best models we could of the grids, and they were provided to us by the different utilities involved. It involved setting up 110,000 bus dynamic, or what we'll call transient stability level model, that combined North America, Eastern and Western grid. Usually we've got about 80,000 bus model for the Eastern grid and about a 30,000 bus model for the Western grid. So we put them together. Then we looked at different locations where the grids are naturally close, and in consultation with the utilities that were helping us out, We connected them. The connections were there were 9 short AC interconnections at voltages between 161 and 345 kV. Sometimes the connections were very simple, such as at the Laramie River generator. The east and the west are actually both right there, and we just had to close a bus tiebreaker to connect them. Other places, they would require a transformer or a short transmission line. The takeaway is we don't see any showstoppers with doing such an interconnect. The key constraint is that during a dynamic disturbance, if the disturbance is in the west, the loss generation will quickly flow from the east into the west, and it will go across your interconnection. When I looked at the circuit diagram of the interconnection from 1970, what surprised me is that they didn't seem to be strongly interconnected. And when I looked at that, I thought, yeah, during a disturbance, a lot of power is going to flow across those few lines, and they're going to have large angle differences, and they're probably going to separate. And that's actually what occurred. In our studies, we connected them with 9 places where they're close, and it's not, we don't think it would be highly expensive to do. I will say some of the results are shown here using synthetic grids. These are fictional grids that we set up just to make it so that we could share a little bit more detail. So we went through the gory details of combining these models. If you work with power system dynamic models, you know there's a lot of gore involved in it. A lot of specifics associated with all the different models. The buses have numbers, and the numbers between the east and the west overlap. So what we did is we just added 2 million to the west numbers, so we avoided that overlap. There's different software packages that are used in the west compared to the east. So we used PowerWorld, since it can support both the west and the east models in doing the simulation. We looked at a couple of different operating conditions. This was a heavy loaded scenario. This slide here, the ovals there show the generation. Here, it's not the capacity, it's the actual generation from the particular model that we looked at. The shading there is just based on how much the unit was putting out. I shaded the ones that were producing a lot a little bit darker than the ones that were producing less. It looks similar to what I showed earlier. You will note that there's a hole in Texas. That's because we did not model ERCOT because they were not part of this study. This was just looking at joining the east and the west. We also looked at a light load scenario. This is one where about half of the generation is not available because the load is half. You might look and see that there's some red on here. We actually, in the US, we have some pump storage hydro, and during light load condition, usually the pump storage hydro is being used to pump water, so it looks like an electric load. That's why I colored them red there. This is the circuit diagram of how we joined these things together. The different colors indicate the different voltage levels used in North America. Green is 765 kV. The orange is 500 kV, the red is 345 kV, and then the blue would be 230 kV. There's a whole number of lower voltage lines that I did not show here, but we had all of those lines included in the model. So the model had a lot of detail, and then we connected them together, and you can kind of see where we're connecting them together there. Our connections went from Montana down to New Mexico, and we had a total of 9 of them. The grids are actually fairly close in Canada. We did model the Canadian portion of the grid, but we did not interconnect the system in Canada. Okay, so then what we did is we set up our dynamic simulations, and then we did a whole bunch of different studies. The model had 110,000 buses. It had 14,000 generators in it. It had 37,000 different types of dynamic models, and there were 243 different model types. that is a lot of model types and a lot of models to use in a simulation. And then most of this project was doing these dynamic simulations, and we used a pretty standard time step, which is a quarter cycle or 1/120th of a second. This slide really gets into the gory details. When you do this, what you find is that there's many similarities between the dynamic models used in the East and in the West. And a lot of times they're completely the same, but sometimes there's subtle differences. So you have to look at the block diagrams for the control systems associated with the different models to find out where the differences are. Here's an example of it. If you know dynamic simulations, this means something. If it doesn't mean anything to you. But it's an ESDC1A exciter model, one of the 200 some odd different models we use, and how it adjusts for the KE parameter, which is a value. It's a gain value. It's shown kind of on the bottom of the block diagram there. Differs from what's done in the East versus what's done in the West. Not one side versus the other side is not correct. It's just the models themselves are tuned for different software modeling assumptions. And when you put them together, if you don't use those same assumptions, you get oscillatory responses. So we had to address these issues, and we did. In doing these simulations, we did a lot of different disturbances. Some of these disturbances are quite short, like you might do a 10-second simulation looking at how does your dynamic model respond to a fault. Some of them were much longer. We might do a 6-minute simulation because we wanted to make sure we didn't have any low frequency oscillations going on in the system, and that we had a reasonable response for the automatic generation control. So sometimes we'd run these out for up to 6 minutes. What we found is that even in severe events, and we did some really severe events, the grids maintain synchronism. So we were quite happy about that. The key issue is the loss of power generation in the West. You get it flowing across the interface, and I'll show that in just a second. The converse is true. If you lose generation in the East, the makeup power will flow from West to East, but because the East is much bigger, the amount of makeup power that flows is much smaller going from West to East. So what are some of the advantages? This response here shows the frequency variation at several locations in the West to a particular generator loss scenario, and the thin lines show the response if the West is on its own, as it currently is. The thick lines show the response if the West is joined to the East, and you get much less. Initially, in the first few seconds, the response is very similar, because the governors in the East have not yet sensed that there is a problem in the West. Electricity flows through the grid at nearly the speed of light. So it flows at a speed that's close to 186,000 miles per second. But these electromechanical propagations go through the grid at a slower speed, but they're still quite fast. They travel on the order of 1,000 miles a second. So within seconds, if you lose a generator in the West, the generators in the East are responding. So that's why we saw those thick lines here. This here is a graph of the interface flow. So it's our 9 interfaces that we added to join the West to the East. And here the sign convention is that East to West is positive. We set it up so initially it has nearly zero flow on it. Then at 1 second, we do a generator drop scenario in the West, and the power starts to flow across the interface. Within 5 seconds, a lot of the lost power has been made up coming from the East. So the East is helping the West, as the West would help the East, but because the East is bigger, it's got a lot more help to give. Now you might look at that, you might say, well, at 30 seconds, it seems like it's settling down to a net change of several thousand megawatts across your interface. Isn't that a problem? Well, in the simulations that we did initially, we did not model the important automatic generation control, which is the response that will ultimately drive the system frequency back to 60 hertz. So what we did is we augmented the simulation to model automatic generation control, or AGC. AGC is driven by a signal known as the area control error. Each of the large balancing authority areas will calculate an A signal. If you're familiar with electric grid names, PJM, MISO calculate ACE signals. ACE has a megawatt component. It's got a frequency bias component. As we did the longer simulations, what we found is that, yeah, the interface flow goes up initially, but then it pretty much settles back to where it was. So if I look at this graph here, after 6 minutes of simulation, the first 30 seconds, what I showed you before, show that following that disturbance, you get that major east to west flow, and then it settles out. And then I set it up to model the AGC response. And in this case, what I set it up so is, in this particular scenario, which was a generator loss in the west, I set it up so that the makeup power is done by generators in the west. So they gradually ramp up over the course of several minutes, and conversely, the interface flow goes down. So in doing this simulation, a key challenge that we had to address is what I would call situational awareness, engineering situational awareness. We were running these gigantic simulations, and even a 30-second study would produce many gigabytes of results. And we were trying to figure out, well, what is actually going on in the system? Because we were covering the whole country, we did not know the exact details of every location in the country. So we might see a voltage going low, and we'd want to figure out where it was going low. So part of this project was coming up with better ways to visualize the response of the system. And here's an example of some of the techniques that we used. Certainly we used time domain graphs. That graph on the left shows all of our bus frequencies. So we plotted all 110,000 of them, or maybe it's substation frequencies, but it's a lot of frequencies over the course of the study. That's just a lot of data, but a nice thing that graph shows is it shows us the envelope of the response. And what was helpful is it was showing us that we weren't getting any strange behavior. Things were staying bounded, and actually they were settling back to a specified frequency. The image on the right here combines a couple of pieces of information. This is for one of our synthetic grids, so I'm showing you more of the numbers here and some of the details, because this is not the actual grid. This is a fictional grid that was similar to the actual grid, but was free from CEII. The magenta box is showing the location of the lost generation. In this case, we tripped some generators in Arizona. The yellow boxes are showing where the generation is being made up. And this is at 10 seconds into the simulation. You can see the generation is being made up kind of across the whole country. The black arrows there show how power is flowing through our grid. The red contour shows the drop in the voltage magnitude. Sometimes when you have these large transfers, you do get voltage magnitude drops, and that was a concern in the synthetic grid, and it was a concern in the actual grid. We talked with the utilities involved and discussed the particulars of what we were seeing in the actual system, and they did not think it was unusual. The good thing about local voltage issues like this is they usually can be fixed without too many issues. But in this particular synthetic grid, a fictional grid, we were getting some major voltage problems in Wyoming. This is an actual grid response. What I'm showing here is the response of the system at 2 seconds. I did a generator drop scenario in a similar location in the Southwest. And then at 2 seconds, the frequency is going down. Now what the colors are showing you is the frequency variation. The scale was on the image, but I cut it off just because I was a little sensitive about the CII. I don't think there's CII in the scale, but I just didn't show you the scale. But what you're seeing with the red is the drop in frequency. When you lose generation, the frequency starts to drop. If it was just the West by itself, it would just drop in the West. But since it was also involving the East, at 2 seconds in, the frequency is just starting to fall down in the East. At 12 seconds in, though, the frequency disturbance has propagated across the whole country, but it's very modest. You can't tell that from the graph, but it is very, very modest. It's like the East barely takes notice of this, except all of the generators across the East have sensed within a few seconds that there was a problem in the West, and they're immediately sending aid. And those black arrows are showing the change in power flows across the system, and it's going across our interface. And that's why you see the interface loading going up, because we get this automatic response from the generators in the East. And then when I run it at 180 seconds, the frequency has mostly come back to where it should, close to 60 hertz. And actually now the yellow ovals are showing where the makeup power is occurring after the automatic generation response. What I set up in the simulation is I had it so that after the loss of the generation in the Southwest, that utility talked to the other utilities that were nearby and said, hey, we need some emergency power. And they purchased power from their neighbors. And that's why you see the yellow ovals going up significantly in the West. I did change the scale on the large magenta oval, because if I had scaled it to be totally proportional to the megawatt loss, it was too big. So I kind of capped it out, but it was a significant loss of power. The takeaway is that within a couple minutes, the interface flow really hasn't changed much. The voltage problems have come back, and we're not in too bad of shape. Just in kind of finishing up here, just a couple comments on these synthetic electric grids. The project had a synthetic grid component, and that was so that we could disclose our results in more detail without compromising CEII. Synthetic grids are something that we've been developing here at Texas A&M, and we have colleagues like at University of Wisconsin who are developing them as well. The Wisconsin people like to call them realistic but not real grids. They're very helpful for research and we use them some in this project, but a lot of this project was associated with the actual grid. The US DOE ARPA-E has been funding work in this area for the last 5 years, and it's very much appreciated. So we made grids that are geographic. That's an example of our synthetic grid that we used in this project. It's an 80,000 bus grid, so it's about the same size as the actual grid. We did make up a synthetic grid for Texas. We've got one that was 2,000 buses, and we've recently augmented our Texas synthetic grid to be 7,000 buses. It's fictional. It uses public data and generator, public data on the load, but all the transmission lines are fictional, so there's no CII. But it's sort of realistic in its response. We contemplated putting our Texas synthetic grid in the study, but ultimately we decided just to match what we were doing with the real grid. There's a lot of static analysis that goes on with this, power flow analysis, contingency analysis. We did a lot of contingencies to look at the static power flow aspects. If you know about power system static response, you know that when you transfer power across an interface that's as big as the one that we looked at from north to south across the country, it matters where you're getting power from and where you're delivering it to. for example, is the power coming from a utility in Colorado and going to a utility in Nebraska? That has a different impact than if it's coming from, say, wind in the Dakotas or the Texas Panhandle that is going into the Arizona, Southern California area. On our synthetic grid, we had a maximum transfer capacity of about 5,000 megawatts west to east and 3,500 megawatts east to west. I'm not saying what our exact values were for the real grid, just because of CEII concerns, but I will say that for our synthetic grid, they were about 5,000 megawatts west to east and 3,500 megawatts in the other direction. And there we had 7 connections. Our connections range from 138 kV up to 500 kV. On our synthetic grid, we again used the AGC response, so we got very similar response. We do have this grid, or we will make this grid available on our website. The website is, if you just Google electric grids TAMU, you will find the website. It's very easy to find. It's a synthetic grid, so we can make it available so people can play around with it. That's a response here to the loss of generation. It has, when you connect the synthetic grids together, it has much less frequency deviation in the west. And when you do eastern interconnects impacts, they really don't have, the fact that you're connected with the west really doesn't have much of an impact on those. Voltage drops, this was, we got voltage drops on the order of 0.3 per unit, but I will say, this is synthetic grid results. This is a triple looking at the dynamic response to the system. And again, we're getting generation made up across the whole system. So what's the conclusion here? The conclusion is, if you're a student, the electric grid is rapidly changing. There's lots of engineering opportunities. I would encourage you, you know, if you're an undergrad, there's lots of opportunities with utilities. Do consider going to grad school. There's many good grad programs available. If you're a grad student, I think you should find good opportunities. On the particular study here, from a technical perspective, we believe the North American Eastern Western grids could be connected with a modest number of AC ties that would allow for stable operation, even under quite severe contingencies. And we did use quite detailed models to come up with that conclusion. This was more of a scoping study, so we did not get down to designing, you know, the particulars that you would do. That would come next. Future work would be looking at and saying, okay, you're saying it can be done. Of course, there's a question of saying, should it be done? Are the economics strong enough to justify doing that? And that's something that we did not fully get into on this project. And then the visualization results for large grids is crucial. I will finish up by saying at Texas A&M, we've got a really cool electric grid control center that we are developing. We are using that control center for studies of high impact, low frequency events, among others. This is a pre-COVID-19 picture of the center. So if you're wondering how come we're not social distancing in there, it's because that was when we didn't have to social distance. And nowadays, I think that room has a capacity of just a few people. We're very much looking forward to inviting y'all to come out and test out some of these simulations. So with that, I'll open it up to questions. And Andrea,
Yes, there is someone who raised a hand, so let me unmute and see if we can voice it in just a second.
Hi, Tom. Yeah, actually, I am unmuted, so maybe I can talk.
Yes.
Hi, Tom. Thanks for your good presentation.
thank you.
First of all, you mentioned half cycle time step for the transient stability. Do you think this half cycle can catch all the dynamics of your transient stability? This is the first question. Half cycle.
Yeah, I mean that answer is quick. Yes, we do think half cycle work. I should say that that's the main time step. Some of the models use a much smaller time step in simulating them.
So it means your parameter for all the dynamic model, the time constant is more than half cycle. It means at least 8 seconds, milliseconds. Do you think that all the generators, all the exciters, all the elements must have, so you already assume that it must have more than 8 millisecond response. So you already assume that. Is it correct? Do you understand what I mean?
What was that?
Okay, so it means you already assumed that all the time step or all the time constant of your dynamic model must be more than 8 millisecond always.
No, what I said is the exact opposite. I said on some of the models, it's much lower than that because of the integration techniques that were used.
That part I don't understand, but okay. So, okay, we'll talk then this later. Second one is you mentioned you used synthetic grid, but in the synthetic grid, parameters are changed, right? Because this is synthetic. So for that such big system, does it make any sense when I run transient stability? Because parameters are changed and you know all parameters are very sensitive. So if I change something, and you know there are also limitation for the tie lines. So for that big system, does it make good sense to run transient stability for 11,000 buses with change parameter?
What we wanted to do on this project was to run 110,000 buses, full dynamic simulation, so that people did not say you're compromising on the system size or fidelity of your simulations. And we ran them out for 6 minutes using AGC response, which if you know about what AGC response does, it's substantially changing the output of some of those generators. So it's we wanted to make sure we were stress testing what we were doing, because we didn't want somebody to say, well, if you used a 200 bus equivalent, we didn't do that. We used 110,000 bus, full model, all the dynamic models, and it worked.
Yeah.
So I've got a few other questions here that, let me just read them here. Let me see. Was loss of generation simulated in your synthetic grid? Yes, we simulated the loss of generation in the synthetic grid. And sometimes in the synthetic grids, we're getting some feedback, Andreas. We might want to be muting people here. One question, yes. Oh, that's a response to that. Will this video be posted online? I'm not sure about the video. We have developed some really interesting videos associated with the response of these grids. If you could mute, that would be appreciated. Thanks. formula that's used. I can't remember the specifics, but the beta value is something like 1% of the load or something. And then we set the each generator to participate in proportion to its MVA capacity. The idea here wasn't to do a particular study of a particular situation. It was to say, if I we're checking out issues with low frequency oscillations. We did get a case where there was one large generator in the east that had, I think it was a poorly tuned PID parameters associated with it that only manifested as you did these longer term simulations. We identified that generator, modified the PIDs, and it seemed to work fine. Okay, one person said, in your modeling, did you keep the existing HVDC ties between the east and the west? What we did, and this was in consultation with the utilities, is we bypassed the existing HVDC ties. That I don't think was a crucial thing to do. We could have included them, and we talked with utilities all along the seam. So we got a lot of good feedback from the participants in this project, and jointly came up with that decision. I don't think it would have had a big impact because the primary issue here was on the dynamics. Okay.
Excuse me, Dr. Overby. Hi. Yeah, this is Vahid. I'm from Opalarity from Montreal. My question is that you said you have the WEC system imported from PSSE and then the Eastern system coming from PSLF. So at the end,
it was the exact opposite of that, and we got the WEC system in the Power World format. The East system was in PSSE format. Okay,
but at the end, was there something like you could export the entire system data in one format that others also can use that? I mean, for example, export
we've got our synthetic grid set up so that we use one common format. And for those of you who know about modeling power system dynamics, you know that different software vendors use slightly different models sometimes. I don't think the modeling differences, I don't want to say they're not significant because they do affect the results. The challenge we have on this is that of those large number of models that we use, some of those are models that are used in the West that Power World supports and PSLF supports. And some of those are models that are used in the East that PSSE supports and Power World supports. Power World supports both of them, but there's not, if we put them out as the DYR file, we're going to lose some of the West models. If we put them out as a DYD file, we're going to lose some of the East models. So that's a challenge. Now, again, we made synthetic models up so that we could get these out to people. The real case, of course, is CEII, so you'd have to go to the individual utilities to get the models anyways, or the cases.
Okay, thank you. And the other thing, you said that you run simulations for 6 minutes for that big system. So how long does it take in your simulation setup to run for 6 minutes?
I mean, we're certainly not running them in real time, if that's what you're asking.
No, I just wondering.
I'm thinking it took on the order of about 100 seconds per second.
Okay,
that's just ballpark. I mean, these are we used a lot of computation to do this. There's no doubt about that. And anybody who runs these knows that your computers are kept busy.
Sure, I just wanted to know. Thank you.
Let me remind everybody that we are at the top of the hour. For those questions that were not answered now, hopefully we will get this from the Zoom meeting, and hopefully they will be addressed later on. And the slides will be posted, and if the condition or if the quality of the recording is good, that might be post it as well, and we will let you know. So thank you, Dr. Rababi, for this timely presentation.
And Andrea,
Yes.
we should announce that we are working on getting our next, this is part of the Smart Grid Center webinar series. And I believe, correct me if I'm wrong, Andrea, our next speaker will be Professor Russell from Texas A&M, and he will be speaking at the end of March, and we'll have it posted on our website. So I do appreciate y'all taking time to join. And if you send me emails, I'll try to answer questions as they come in. So thank you for joining, Andrea. Thanks for all your work in setting us up as well. So
thank you, and stay everybody safe.
bye.
Bye-bye. Goodbye.